Welcome, everyone. Hope you're having a good time so far. So today we're going to be talking about this monad transformer state, whatever that means, and everything you didn't want to know about it. So I'm very impressed that people showed up, even though I gave it a scary-sounding title to the talk. So I already asked, oh shoot, that was bad. So I asked a little bit earlier if everyone knows what a monad transformer is. Looks like there's a pretty good idea, but I want to redefine a monad transformer before we get started. A monad transformer is something that you use to add extra functionality on top of an existing monad. It's a convenience mechanism. You could get this functionality some other way, but we're doing it for convenience. And the canonical example, and you'll see why it's canonical, we're going to use it a lot in this talk, is reader T, which is just a nice, easy way to avoid passing extra arguments to functions. There are other things. Bartosz's talk gave some examples of other reasons you may want to use a reader, but for our purposes, it's just a convenience. And then we're also going to be talking about this thing called environment and state and how that applies to different kind of monad transformers. In this talk, we're going to be talking about three different transformers: reader T, state T, and accept T. Those are the ones we're going to be talking about explicitly. There are also a few others that are basically implied by this. So identity, T, and writer, all of these are implicitly covered since these, those four that I've listed and a few others, those are all isomorphic. Those are all can be expressed in one of those previous three. Things we're not going to be talking about today are continuation-based transformers. Those are things like cont or conduit or pipes or things like that. We're not going to be getting into those. Those are more complicated, and I'm not even going to really get into why they're more complicated here. We're just going to pretend like they don't exist. So if you ask me a question, I'll just say, talk about it afterwards. And then the other simplification we're going to do is we're only going to talk about one layer of transformers. I'm sure people have seen these crazy deep monad transformer stacks, reader T on top of writer T on top of state T. We're going to pretend like those don't exist either, but it's not very much of a leap to go from what we're going to talk about to those. So these are the three transformers we're going to be talking about. And pay attention, all of them are new type wrappers around something going on with the underlying monad. Or if we want to specialize it, which we're really just talking about I/O today, if you want to specialize it, you can go ahead and you can look at this as a reader is just a function from R to I/O of A. State I/O is just from some state to an I/O of a pair of an output value and a state. And accept T is just an I/O wrapped around an either EA. Keep that in mind as we go through this, and we will be revisiting these definitions a little bit later. Okay, so forget about transformers now that I've given you that great introduction to them. Forget about them completely. We want to do a very simple concurrency problem because concurrency is so simple to do. We have two different functions. We've got foo and bar. Foo and bar both live in I/O, and they return A and B. And now we want to run these two things in parallel, or concurrently. We want them to run at the same time, and we want to get a pair of the two different results. How do you do that? Well, fortunately, you don't really have to do anything because there's this great library called async. If you don't know about the async library, go read about the async library. It's a great library. We just use that library. It provides this function called concurrently, and it magically happens to provide exactly the type signature that we're looking for, and everything works. Everyone can try to guess why I chose this example. In reality, though, it's very unusual that you're going to have functions that are just lying around. They're not really functions, they're actions. They don't have any kind of arguments. Usually, you're going to want to pass in some kind of value. So in our example, I've now made this slightly more complicated. Foo and bar, instead of just being IOA and IOB, take this myEnv. And myEnv is some kind of environment that's getting passed in. And then our baz function is going to call, again, these two functions in parallel. How do you do it? Well, it turns out that this isn't particularly complicated. You just go ahead and you capture that environment as an argument to the baz function. You pass that into foo and bar, and then you run concurrently again. And this is pretty straightforward usage of everything that you're used to in basically every programming language on Earth. So this shouldn't be too complicated. Of course, we're Haskellers, and therefore we like to make things more complicated for no reason. This works, but I'm really, really irritated about this fact that I had to explicitly pass in an argument. That just irks me. Let's get rid of it. Who here can take a guess what magical technique I'm going to use to get rid of that extra argument? Reader T. Cool. So now we don't have functions anymore. Now we just have reader T actions. And the myEnv thing is still floating around, but it's being taken care of for us automatically. And that simplified everything. Now we don't have those ugly little arguments floating around, and everything works, except for the fact that the code doesn't work. If you try to run this, if you try to compile this, it's going to fail. And it's going to fail for a very simple reason. Concurrently is expecting you to give it an IO and an IO. Instead, you're giving it a reader T on top of IO. So this thing just doesn't type check. So as much as we wanted to simplify things, we've actually made it more complicated. Question is, can we get our BAS function to work without having to change concurrently? Fortunately, we can. If you remember way back in one of the earlier slides, reader T is just a new type wrapper on top of a function. What we're going to do is we're going to unwrap and rewrap that new type wrapper. So we've got foo, and now we've unwrapped that reader T. Now we're back into that previous state, Now we've gone back to this kind of representation, where it's going to be a function from INV to IO. And we do the same thing with bar. And then we use this reader T constructor to capture our environment again. And we pass it into concurrently foo bar. And basically, we now have a long, ugly version of the same thing we had before. But we prove that we can do it with a monad transformer, so that's kind of cool. But I don't really like this. I mean, does anyone think that this is nicer than what we had before? I don't think so. We also have this alternative way of doing this. We can, instead of dealing with the reader T constructor directly, we can use the ask function to go ahead and grab the environment. We can use run reader T to unwrap foo and bar. And then we can use the lift function to take the resulting IO action and turn it back into a reader T action. And this is the same thing that we had before, and now I've put it into this helper function, concurrently R. And that's great. Now we could use concurrently R everywhere that we were previously using concurrently, and things will just type check. But there is a real problem with all of this. The question is, do you want to have to redefine every single function through your entire code base every time you want to use a monad transformer stack? That seems a little bit tedious. So instead, it would be nice if there was some way that I could write concurrently so that it worked on lots and lots of different monad transformers, or monads in general. So the question is, can you do that? Answer, of course, is yes. And you can use this package that already exists and has been around for a while called lifted-async. Lifted-async provides a lifted version of the concurrently function, and it uses this thing called monad-based control, which is magic. We'll cover it a little bit more later, but now it's just magic, and it makes things work. It makes things work for various levels of transformer stacks. And it works for reader T and state T and a bunch of other things. And now you're able to pass in your reader T actions and get back a reader T action with the tuple. And this is exactly the magic that we were looking for. And I keep using this word magic because magic is scary, and you should be scared. So this works, and looks like we could use it for state T as well. So let's give it a shot. Take a look at this program. Think about what you'd want the output to be, and then look at what I tell you the output actually is. So what we're doing here is we have this helper function putter. It starts off by updating our monadic state for the state T transformer. It's updating that with a new value of 2. Then we run concurrently, and in these two separate threads, one of them is placing a new value of 3, and one of them is placing a new value of 4. Then in our main function, we run this thing, and we try to look at what the resulting state is at the end of all of this. There are 4 numbers on the board right now, 1, 2, 3, and 4. I can't make a good argument for why 1 should be the answer. 1 doesn't really make sense because we put 2. But 2, 3, and 4, interesting. No one would probably guess that 2 should be the answer, but between 3 and 4, how do you choose which of these threads win? It always gives you 4, surprisingly. I also thought that there would have been a race condition involved here. No race condition. So what's going on? Why is it that we've just chosen that the second thread wins and the first thread doesn't? In order to understand what's going on, let's forget about the lifted-async package and try to write this concurrently for state ourselves. Oh, sorry, we're going to look at one other example before we do that. Another example is this bracket function. Bracket is a function in Haskell that goes ahead and lets you acquire a resource, clean up a resource, and in between, do something with it. This is really good for exception safety. For example, if you want to open up a file, do something with the file, and then close it afterwards, bracket is a great function to use. So in this case, we're saying we're going to have this state, which is a list of strings, and the acquire action that we're going to do is going to add 1. The cleanup action, the inner action is going to add 2, and the cleanup action is going to add 3. The question is, what is the result of this? Problem is, it's a trick question, because there are 2 different implementations of bracket that work for state T in common libraries. One of them is going to give you a list with just 2. That's the lifted base that we were using on top of monad control. In exceptions, a different package is going to give you 1, 2, and 3. So now we've come up with 2 completely different sets of semantics for the same function for the same type, which is a little bit scary. So now, let's actually implement concurrently directly. Forgetting about all kinds of type classes, we just want to implement this thing ourselves. We're going to use the same technique that we used before for reader. So we unwrap state T, we get f and g, these 2 functions. These are going to be functions that take an input state and give an output state and a result value. Then we capture S0, which is going to be the initial state. And if you look here, we're going to go ahead and capture A in S1 and B in S2. And these are the output states that come from the 2 child threads. Then we're going to choose that we're returning S1 as the new state. Who can think of 2 other options that I could have chosen to put in there instead of S1 to make things type check? S2 or S0? I could have chosen any of those 3. We've arbitrarily chosen S1. It turns out that the monad control pack or lifted base package has arbitrarily chosen S2 to be the solution. This is what we call discarding. We are arbitrarily choosing to discard some of our state, and that should scare you. You get essentially the same thing with bracket, except it's a little bit more insidious. It's harder to see here. When we're implementing bracket, we start off with S0, and we pass it to our allocation function. Let's say that our allocate function updated that state. Now we go over to our inner function, h. Which state does h receive? Does it receive the state that was created by the f function? It doesn't, because we're passing it in S0 again. And the same thing with g. So if you do things in the most direct way possible, you're going to implicitly end up throwing away state transformations that are going on in your functions. And this is the problem that we're getting at. So we talked about state T. Let's throw except T into the mix. Again, we're going to implement concurrently. With except T, each one of our child threads has 2 possibilities. Either it's going to return left, usually meaning something went wrong, or right, meaning everything went okay. And yes, you can use except T for things besides failure, but we're going to just pretend like it's about failure. If you get 2 right values, then the solution is obvious. You go ahead and you return a pair of the 2 values. If you get a left and a right or a right and a left, then you throw away the right value and you return the left value, which again is the only logical thing you can do. The problem is this final case, where you have 2 different error values that are coming out and you have to choose one of them. Again, we're going to be arbitrarily choosing one of them and throwing away the other one. So we have the exact same problem that we had with state T. Here's the important thing I want to get across. I am not talking about some kind of a bug in the implementation. No one can open up your laptop right now and send a pull request to the lifted base package and say, or the lifted-async would be a better example. Send a pull request and say, I can solve the problem with concurrently. It can't be done. This is inherent to the algorithm that we're trying to implement. The problem is that there are certain classes of functions and there are certain classes of transformers, of monad transformers, that will always end up having some kind of problems around discarding. And now we're going to try to figure out what those classes are so that we know what to avoid. On the function side, we have these things called control functions. It's not the greatest term in the world, but it's basically the term that is floating around, so we're going to use it too. Control functions are functions which receive I/O actions, or M if you've already lifted it, the arbitrary monad, as input instead of output from the function. Another way of putting this is that they are contravariant in the monad, or that the monad appears in negative position. These are common terms that are used. I have a blog post up when you You can click on that if you look at the slides later. So if you want to get a feel for what those terms mean, you can go ahead and look it up. But basically, the simple intuition is if the I/O appears as input, then you have a control function. Control functions can't be lifted directly with the lift function or with lift I/O. So let's go ahead and work through some of these to understand what's a control function and what isn't. So put strlen has I/O appearing only as the output from the function. It's only in positive position. And that means that you can simply do lift I/O on the result of a put strlen, and now it'll run in a state T or a reader T or anything else on top of I/O. So therefore, this is not a control function. This is simple, and you can lift it without any kinds of problems. Fork I/O, on the other hand, has an I/O in negative position. It's the input to that function. And therefore, no matter how much you play around with lift I/O and lift and monad trans and monad I/O, you will not be able to convert fork I/O into something that works on state T. At least not directly, not without playing with the innards of state T. Catch and try both take I/O actions as input. Catch takes two of them. It takes both the initial action and a cleanup handler, or an error handler, and try has one of them. Atomic modify IORef, you might think that it's an I/O action, but that's just an IORef as the input. There are no I/O as input, so it turns out that atomic modify IORef, you can just lift I/O and you'll be safe. Modify mvar does have I/O as input, so that one you can't lift I/O. Now let's talk about the different transformers that these things are going to apply to once we start analyzing these control functions. So again, I told you at the beginning I was going to come back to this. We've got reader T, state T, and accept T. If you look at reader T, that R type parameter is oftentimes called the environment. And it's an environment that is read by the body of your function, but you can never update it. And that's the beauty of reader T. It's read-only, and that's what turns this thing into an environment as opposed to a state. It's readable, not writable. And another way of putting that is there's no mutation going on with it. State T also has S, just in the same position as R, as input. But it also has it as output. And since you can change it throughout the body of your function, state T has state, which given the name of it, I guess isn't really surprising, but we need to point it out. So it's got both an environment and state. Accept T kind of looks like it doesn't have any kind of state associated with it, but it does. The either that's wrapping up the A is indicating whether something succeeded or failed, again, using our definition of what accept T is supposed to mean. State T and accept T both have this mutable state. As you go through your function, you are updating something that's sort of mutable. It's technically not mutable, but we're treating it as mutable in the body of our function. As a result of that, these things have state, and therefore, we were unable to implement concurrently for those. It's not accidental that concurrently was able to work for reader T without any kind of problem. Because reader T is missing the state, we're able to implement control functions there without any issue. Unlifting is a term that I've made up, and we're going to use it. So it's just as made up as control functions, and you can hate the term. I don't care. Unlifting is what we're going to be doing to control functions. Normal functions that just have I/O as output, you can lift. Unlifting is where you're going to have to do two steps. Instead of simply taking the output that's an I/O and lifting it up, you're also going to have to take some kind of input action, knock it back down to I/O, and then after you've run your function, you're going to lift it back up. We saw that with concurrently. Concurrently, when we were doing it on reader T, we started with an input action, which was in reader T. We knocked that down to just I/O by giving it the environment that it needed. And then at the end of running that, we lifted it back up. That's the general pattern that you're going to see with unlifting. Any transformer that has no monadic state can be safely unlifted, can safely unlift control operations. And the problem is that transformers that do have monadic state may end up requiring discarding of some of that state when you're doing unlifting actions. So is reader T really that special, or are there other things like it? It turns out that there are lots of things like reader T, but they're all isomorphic to it. Anything which just has some kind of input value can work like this. Identity T is an example of that. Turns out that identity T can be represented as reader T, where the environment is just a unit value. In other words, we don't care about it. Logging T is something. Logging T and no logging T are both things from the monad logger library. Both of those work in the same way. So if you're able to take your monad transformer and somehow represent it in terms of reader T, you're going to be safe, and you're going to be able to do this unlifting. Now, there are other cases where you can actually unlift a control function even into something like state t without worrying about discarding. And I want to give you a few of those examples to make things clear. So try is one of those examples. It only has one input function. And since it's only got one input function, it's only going to end up generating one new updated state. And therefore, you can run this action, and then you only have one newly created s value that you have to deal with. You may also notice, though, that in this left case, where an exception did occur, we're going to have to revert back to the original state. This is one of the fun things about dealing with the runtime exceptions in the state t transformer. There's no way to catch, to figure out what the intermediate state was if a runtime exception occurs. Another possibility is that you have multiple inputs, but there's a natural linear call path. You're going to be calling this, and then that, and then the other thing, and you don't have to worry about some kind of weird ordering going on. Catch is an example of one of those. So you've got the main action, and then you've got your error handler. And the error handler is only going to run after, in the event that an exception occurred when running the main thing. And we're going to end up having a very similar situation like we had with try. In this case, we're going to use the updated state from f if it succeeded, and if a runtime exception occurred, then we're going to reuse the original s and then take the new state that's updated from the error handler. The finally function is different, though. Even though finally looks pretty much like catch in the sense that it has a main action and then it has something to do in the case of an exception, it's not just in the case of an exception. The finally cleanup thing also runs in the case of a success. The question is, what do you do with that updated state? If you implement finally the way that I did in the first line, that's actually not going to work the way you would expect. F is going to produce a newly updated state, but G is never going to see it. And the newly updated state that comes out of G is never going to be returned to the outside function. In essence, all of the state modifications that go on with G are just thrown away. Again, we have this discarding. Turns out that if you try hard enough, and I consider what I did here trying pretty hard, if you try hard enough, then you can, in fact, make finally work, but you have to re-implement the entirety of the finally logic when you do it. And this, in my opinion, is a very dangerous thing to do. Once you start having to pull out mask and restore, I'm guessing most people here don't even know what mask is doing, which is better. It's better if you don't have to think about those things. This is a complicated function to have to re-implement. I would rather be in a situation where I can just rely on the finally, which is provided by core library functions. And then, so the actual problem cases are things like finally, where you can technically make it work the way you would expect, keeping track of all your state updates, but it's a pain. Or things which actually have no solution at all. And concurrently is one of those examples. Since there are two states that are created from two different threads, you have no way of combining these together without throwing something away. There is another approach you could take. You could cheat. And you could say, for example, with this bracket function, instead of using MA and MB, I'm going to use IOA and IOB. And the magic that I've created here is now there is only one M as input to this function. And therefore, there's only going to be one newly updated state value that I have to worry about. And if you do this, then you can, in fact, write a safe version of the bracket function for state t. Problem is, this isn't the type signature that people are expecting. People want to be able to access their mutable state inside of their cleanup and allocation functions. So this works if you're able to get away with it, but usually you can't. Okay. At the end of the day, people do want to deal with these functions inside of their monad transformer stacks. So how is it that you should do it? I'll first talk about the two existing solutions which I mentioned earlier. One is the exceptions package. The exceptions package defines MTL-like type classes for each one of these operations that you'd want to do. So there's a monad throw type class, and it tells you how you're going to throw an exception. And there's a monad catch, which tells you how you're going to catch an exception, and so on and so forth. The big downside with, now, when you have something like this, you can technically figure out a way to implement all of these functions correctly for all of the different transformers you're dealing with. The problem is that you have to have an extra type class for each and every one of the operations you want to deal with. It's tedious. And you have to be very careful that you implement the logic correctly for each and every one of the instances that you're going to write. The other approach is monad control, which defines this generic way to, and if anyone here can look at that type signature and figure out what it means, I'm very proud of you. I can't do it. What it's doing is it's allowing you a way to do that knocking down, running things in I/O, and then knocking back up that I was referring to earlier. This code is difficult to understand. I've seen, myself included, many coworkers, many customers I've worked with. No one really looks at this type class and understands it off the bat. There was a very crazy bug. I have a reference to it at the end of these slides. Very crazy bug that I saw where actions were just disappearing off the face of the earth because of an invalid instance of this type class. This is complicated stuff. And if you use it, you're going to implicitly be running into that discard behavior. All the discarding we were talking about with bracket and concurrently come up when you're using monad control. So to work around those problems, when these problems actually occurred, I worked with some coworkers. We came up with a new library called unlift.io. And unlift.io takes a different approach, slightly different approach to monad control. Instead of working on a whole bunch of different monad transformers, it only works on a small subset of them. So we have this ask unlift.io function method, and it says, I'd like to be able to figure out some way that I could take an a transformer action like reader T on top of I/O and run it in I/O. And then you can just use lift.io to lift it back up. This works very well for reader T, but if you try to implement it for state T or accept T, you're going to fail. There are some type class laws that are associated with this, and there's no way that you can implement this correctly. And this is by design. You might say, wait a second, I really want to be dealing with state T and accept T in this case. What we're saying is, no, you're not allowed to do that. We are intentionally blocking you from being able to do something like that. There are similar approaches that have been used previously with monad control. If you go look at the lifted-async package, there's a safe module that does the same kind of thing. But unlift.io, for various reasons, is easier to play around with because it's not using advanced type-level techniques. All right, so assuming at this point I've convinced you that it's dangerous to run control operations in things like state T and accept T, you should have a question. Lots of people write applications that do all this stuff. People, unfortunately, do have mutable state. People want to track their exceptions with something like accept T. So if I'm telling you you're not allowed to acquire, read files, or do a whole bunch of other things inside these functions, what is it that you're supposed to do? My first comment is using these transformers in the small. So in a small subset of your program is fine. If you want to use a maybe T to avoid having to do a whole bunch of pattern matching on, and checking if something is a nothing or a just, that's going to be fine as long as you're not running the control operations. But as soon as you get into a state where you want to start forking threads and you want to start dealing with exception safety, I think you're in a dangerous place using state T and accept T. Instead, my recommendation is for the large application, for your code overall, this is what I'd say is a Haskell best practice for a project, you want to keep your stuff in something that looks like reader T, or a blog post I wrote recently was about the RIO monad, RIO, the reader IO combination. If you do that, then you automatically avoid all of these discard problems. But again, the question is, how do I deal with that mutable state that we have to deal with sometimes? This is the part of the presentation where you get ready to throw tomatoes at me because you're not going to like what I have to say. So as much as we hate mutable variables, I'm going to tell you you should use mutable variables. The caveat on this is don't use mutable variables if you don't have to. If you're able to structure your program that it doesn't require mutability, you're better off. But the idea that you are going to be immutable and but you're going to use state T is a contradiction. State T is technically not mutability, but it's basically mutability. It's going to feel like mutability. It's going to act like mutability. So if you have an application that's doing something mutable, just bite the bullet, accept the fact that you're doing something mutable, and use a mutable variable. On top of the fact that you get to avoid all of these wonderful problems about state discarding, there are a few other things that come along with this as well. I made a reference to it earlier. If you have a runtime exception that gets thrown and you're inside a state T, there's no way that you're able to capture the state that existed at that time. So one of my examples for this is, let's say that you're writing a web server, and you're going to use runtime exceptions to represent a redirect. And let's also say that you want to keep track of things like session updates and headers that you're going to send to the user, and other things that are mutable state. Well, if you use state T to keep track of those variables, there's no way that you're going to be able to keep track of those updated headers and those updated session variables. So instead, use a mutable variable. The other thing that's very nice about mutable variables is you can make them work with multiple threads. State T, by design, will not work with multiple threads. But there are multiple different kinds of mutable variables you can use. So if you pull out a TVAR, you pull out STM, software transactional memory, you can go ahead and write robust, great programs that are going to spread across multiple threads without any kind of problem. So that's the first set of tomatoes that are going to be thrown at me. And the second is use runtime exceptions. You've got a lot of people want to use except T, and there are lots of arguments around it. It's about checked exceptions versus unchecked exceptions. Is it more type safe, less type safe? Here's the argument I'm going to give you. At the end of the day, if you have to deal with the control functions, except T is going to make your life difficult. And it's not going to be giving you any kind of extra guarantees, because the I/O that lives underneath the except T can throw any kind of an exception anyway. So you're stuck dealing with the fact that Haskell's runtime system has unchecked, untyped exceptions. Just deal with it, accept it, love them, and deal with everything in I/O possibly blowing up in your face. I will make the strong caveat that lots of people out there disagree with me on this one. Lots of people think that this is crazy and you should use except T. Definitely up for any kind of discussion people have on it, but this is the recommendation I give. All right, so the conclusion is, state T and except T are great transformers, but they shouldn't be used in the large for your entire application. You should avoid doing things that are going to silently discard state, because it leads to strange, surprising behavior. And therefore, you should stick to when you're dealing with control operations, I'd recommend using unlift IO. I would recommend sticking to reader T and things like that. These aren't nearly as elegant and as beautiful as saying, well, I have no mutable variables, everything's in a state T, everything is pure. That's cool, that's awesome, but if it doesn't work, it doesn't work, don't do it. This talk was based on a lot of different bugs that popped up in the real world and spawned a lot of different blog posts. So if you want to look at these later, this goes into a lot more detail on some of the things that I've talked about, and I'm sure links to the slides will be available afterwards. Okay, that's the end of the talk. Any questions?